All right, so we are on to amides. And as we've talked about all along, all these carboxylic acid derivatives have different stabilities, different electrophilicity. Amides are the most stable derivative. So blank of water is required to force the equilibrium to the carboxylic acid. So we'll even say the blank of water slash acid is required to force the equilibrium to the carboxylic acid. So a heavy excess of those things can push the equilibrium that direction. So how might that happen? How would we force it that way? And why are we able to say that this is an arrow that is a single direction arrow? Well, let's walk through the mechanism of how these things might react, and then we'll readdress that question. So we have heavy excess of acid in water. That means we have sulfuric acid or H3O plus around. We'll just do H3O plus. And we know that strong acids will protonate carbonyl derivatives at the oxygen. So essentially, we would see something like this happen, where we protonate that oxygen, and that makes this position more electrophilic. There's a bigger partial positive at that position. So what nucleophiles do we have in solution that can add there? The only ones we have are water molecules. So essentially they will add to that position, putting the electrons onto that oxygen, forming our tetrahedral intermediate. So we'll put that down here. Okay, so we have our oxygen that's positively charged. All of these are equilibrium arrows still. And essentially at this point we have to say, well, what can this hydrogen be transferred to? We could transfer it to the other oxygen, but what else? We also know that nitrogen has a lone pair. And if nitrogen were to grab that proton, it would provide an intermediate that looked like this. And at this point, we have our tetrahedral intermediate that could collapse back down. And if that happened, we would be putting the best leaving group out. And at this point, the best leaving group is actually NH3. So the electrons could come down and move that NH3 group out, which would provide us with the carboxylic acid plus NH3. So at this point, we have to think, well, what else do I have up here? I have the carboxylic acid as the product, and I have this NH3 and this NH4 as A or B. So are we going to have NH3 be the other side product of this reaction, or is it going to be NH4 plus? So think about that for a second, and then pause it, decide, come back. You did all that. You recognize that this is a super strong acid here. It looks like hydronium ion, oxygen with 3 bonds and a hydrogen, but it's going to be even more acidic than that since it has this oxygen attached that is inductively withdrawing from it. Strong acid anyway. We have an acidic proton. We have nitrogen, which is a base, and that base would come and grab that proton, and that would produce that and that. Ammonium is going to be the byproduct of this reaction, not NH3. If we had NH3, multiple things, right? NH3 would just deprotonate the carboxylic acid, and also we're in an excess of acid. We have extra acid around than what we would need. So any time that there's excess acid around and an NH3 molecule, that proton transfer is going to occur because it's downhill in energy. Again, This is technically the more stable carboxylic acid intermediate, and that's true. But when we are facilitating things with this excess acid, it will at some point force the NH3 out as the leaving group. And once that happens, that NH3 will protonate and form this quaternary ammonium species. And that is how we hydrolyze amides to carboxylic acids under acidic conditions. And again, let's note that it's acid promoted. So we used a full equivalent of acid. Where was that equivalent? Well, for this to be fully NH4 from what we started with, a full equivalent of acid was used in that protonation step. So again, acid promoted, not catalyzed this time. So we can do base, so acid promoted amide hydrolysis. We can also do base promoted amide hydrolysis. And let's take a minute before we even talk about the mechanism to just think about the products. So we have a carboxylic acid or a carboxylate, A or B, plus our amine as our leaving group. So which of these are going to be the product, A or B? You took a minute to think about it. You're done with that. Hopefully everyone predicted B would be the product, right? We're under basic conditions. We have excess base in solution, and there is some slight modifications from the course packet. This was not initially negatively charged in the course packet, and this didn't say OH minus, it said water. But hopefully you adjusted it as I had it on the screen right here. But anyway, we're under basic conditions. This is a carboxylic acid. An acid is going to react with a base if it's an acid. So the products of this reaction are going to be those two things. So how are we going to get there? Just like lots of reactions that we've seen with carbonyls, the carbonyl carbon is partially positive, because the oxygen and the nitrogen are pulling electron density away from it. And the OH minus will add there initially, to generate this tetrahedral intermediate. And in these conditions, essentially if we think about what's happening here, so what could happen next? The things that could happen next are we have our tetrahedral intermediate, the electrons go down, and they're going to kick out the best leaving group, right? So what's the better leaving group, OH or NH2? So if they kick out OH minus, that would bring it back to the starting material. And how can we compare the leaving groups? Well, we can compare the stability of OH minus, and just because we are going to look at what's over here too, we would compare the leaving group ability of NH2 minus. So what's more stable, OH minus or NH2 minus? So we can look at the stability of those based on the pKa's of their conjugate acid. So the conjugate acid of OH minus is H2O, which has a pKa of 16-ish, 15.7. And NH2 minus, its conjugate acid is NH3, which has a pKa of 38. Yeah. So this is so much more acidic than this. This is a terrible leaving group. So yeah, the stronger acid, the more stable the conjugate base. This is a super weak acid, which means this is a very reactive, very strong, angry base. It doesn't want to act as the leaving group. So the reality of the situation is that under these basic conditions with this excess base around, this equilibrium here, the electrons coming down and kicking out the OH minus, so those electrons come down. I'll put like a dotted arrow they can also come down there and kick this out. The red arrows happen 99.999% of the time, right? This equilibrium is very fast and rapid. We're forming the tetrahedral intermediate. It's kicking out the OH minus. Forming, kicking out, over and over and over again. But every once in a while, and I'm putting this big black arrow up here because the equilibrium would be far to that side. Every once in a while, so 0.0001% of the time, the NH2 acts as the leaving group. And both of these, both step 1 and step 2, 1/2, are highly uphill reactions. We're forming things that are much less stable. So we're going up in energy and up in energy again. So not very favorable. But this is somewhat random. Like the more stable thing is going to happen most of the time, but some of the time this reaction pathway is going to happen. It just has to happen every now and then because we know that this works. And once that does happen, what do we have? We have a really strong base. This is a stronger base, substantially stronger than OH minus. And we have a carboxylic acid. So as soon as this acts as the leaving group, it's immediately going to deprotonate that carboxylic acid in a unidirectional arrow sense. This is step 3. Step 3 is a downhill reaction. So sure, step 1 and step 2, way uphill, very unfavorable, but if step 2 ever happens, the next step is going to be an extremely downhill acid-base transfer reaction. So even though this happens very rarely, every time it happens, it siphons off some of the material. It's like, oh, we just took 0.0001 again and again and again. And with enough energy, with enough time, this will occur and this reaction can go to completion. So again, first 2 steps unfavored, third step favored. But if we give it enough time, it can move in that direction since we do have the third step that is downhill, and this third step is irreversible. These steps are reversible. This is an irreversible step. Why is it irreversible? It's irreversible because of the enormous difference in these pKa's. This pKa is 5, this one is 38. pKa 38. The equilibrium moves away from the stronger acid. This one is immensely stronger than that one. So, and a bigger difference than what we just talked about with the OH minus stability versus the NH2 minus stability. So there it is. 2 ways to form carboxylic acids from amides. Great.